for all those who have registered, or even if who are really trying to reach out based on our link. Today we will have the 36th, distinguished lecture, and the lecture will be given by none other than Professor Dipti Ranjan Sahoo from IIT Delhi. Professor Sahoo, he actually passed from IGIT Sarang. Then actually he has done his master's, PhD. For some time he was working in IIT Bhubaneswar, and later on actually he has shifted to IIT Delhi. And one most important aspect of Professor Sahoo is, at this young age, he has got the Bhatnagar Prize. He was one of the Bhatnagar Prize winner, and possibly in history, in the history of this one, no civil engineer so far has got Bhatnagar Prize. Others have got it, but not any civil engineer. But it is a matter of great pride that Professor Dipti Ranjan Sahoo, he has got actually the Bhatnagar Award, and he will be talking about anti-seismic devices for earthquake resilient infrastructure. Very, very pertinent, because of actually earthquake. Every year, so much of actually devastation is taking place. And if the devices which Dr. Sahoo has designed and he has taken also the patent, will help us a lot. So I do not know whether we have the Vice Chancellor, Professor Nanda, present.
Yes, sir. Sir is there, sir.
Oh, she is there. Okay, very good. And how about from IMMT and IIT?
So they have got some important work. They have replied in your email that they'll be not able to join.
Or they are not able to join?
Neither
Okay,
and IIT Bhubaneswar, right, sir?
Okay. I believe actually those people who can join, either they might have joined or they will be joining soon. So before Professor Sahoo gives his presentation, I request our Honorable Vice Chancellor, Professor Pradipta Kumar Nando, to say something about SOA, because SOA is actually hosting all facilities that we are enjoying from SOA. Then he is the right person to say something about SOA.
Sir, namaskar. Good afternoon, sir. Welcome.
Namaskar.
Namaskar. Sir, I think I'll be brief. This we have all of us know about SOA, so I don't think I should. Sir.
No, it may be for those people who are really joining for the first time.
First time, sir.
It can be very short.
Very short. Good afternoon, everybody. Esteemed chairman of this board and chairman of this INE chapter, Professor Damodar Acharya, and the distinguished speaker, Professor Dipti Ranjan Sahoo, all the distinguished fellows and members of INE, Dr. Renu Sharma, our additional dean, are also the coordinator for this, and director and vice chancellors of director of IIT Bhubaneswar, director of IMMT, and others. So about SOA, I think it is known. Nevertheless, it is a deemed to be university and became university 2007, started in 1996. Currently, you have 16,000 plus students and 1,400 faculty members, 5,000 supporting staffs. And we have 60 research labs and 20 dedicated research centers. We have 1,364 PhD students, 500 full-time students. And we have been ranked in NIF ranking 15 last year, waiting for the result this year. And also QS and THE, we are in THE SCI, we are there 300 to 350. THE also we are there in World University ranking 800 to 1000 bracket. QS is 1200 to 1400 bracket World University ranking, and 400 to 450 QS SCI ranking. And we have 139 collaborations with the Indian as well as abroad universities and industry also. We have many adjunct professors from abroad as well as from Indian professors with our university. And our publication is total publication now is more than 12,000 Scopus Index publications, 7,500 Web of Science publications, and we have per year 1,800 publications per year we have from different institutes. We have 10 institutes under the ambit of this university, right from engineering, technology, medical science, dental science, and also veterinary science, agriculture science, law, hotel management, pharmacy, biotech, nursing, etc. So this is a brief about our university. Thank you.
Okay, thank you very much, Professor Nanda. Now, actually, I request our today's distinguished lecturer, Professor Dipti Ranjan Sahoo, to make his presentation, his biodata, and even abstract of your his talk. It is already circulated. At least we might have really gone through. So therefore, we are not taking much of time in that. So without any delay, I will request Professor Sahoo to make his presentation.
Thank you. Thank you, Professor Acharya. I think I'm audible to all and the screen is visible.
No, it is, you are perfectly audible. I may not be.
No, okay, thank you, sir. So first of all,
make full screen. Full screen, if you can make it.
Yeah,
I
did
good.
it. Okay. So first of all, I would like to thank INE Bhubaneswar chapter for giving me this opportunity to deliver a lecture under this distinguished lecture series, which is jointly organized by SWA, IIT Bhubaneswar, CSM, IMT Bhubaneswar, NISER, and IEEE Bhubaneswar. I particularly, my sincere thank actually I want to extend to Professor Damodar Acharya and Professor Ganpati Panda. So both have been actually pursuing me for this lecture. Although I said that I will take it, but because of the teaching and other commitment, slightly delayed. But I said that I will deliver this lecture as soon as the teaching commitments are over. So today is that day, and it is really a privilege to be here. And I also like to thank the audience who have joined this presentation. So the topic today I'm going to present is the anti-seismic devices for the earthquake resilient infrastructure. In this lecture, I want to highlight most of the things which we have done towards the to increase the resiliency of buildings and bridges in the event of earthquake shaking, and we have developed some of the cost-effective devices to take care of the seismic effects. So I will present that in this lecture. Before I go to the my actual presentation, I take this opportunity to thank my students, my research scholars, my staff members, my colleagues at IIT Delhi, family, parents, and the sponsoring agency and collaborators in India and outside India also. So this is today's outline. I'll start with briefly what is earthquake, what are the effects to what we are today, that is called the current practice, in which direction we are moving to make our infrastructure seismic resilient. And then there are some practical applications of the devices I will be explaining today, and what are the challenges ahead, road ahead, particularly interesting for our young researcher faculty members who are actually interested in taking up this area of research as their career option. So as we know that the earthquake is actually a result of some uh, kind of release of energy due to breaking of some plates. It may be within the plate or maybe sliding between two plates, which actually occurs few kilometers below the our earth surface. And where it actually happens, we call that is focus here. And if we directly see on the earth surface, we call the epicenter. So the focus is the point where there are a lot of energy is released, and that energy release actually uh, transmit all around in terms of the waves. And these waves actually pass through the body of the earth. So that's called primarily called the body wave. And once it is actually reaches at the crust of the earth, it's called the surface wave. So in case of the body wave, there are two things. One is called the primary wave and one is called the secondary wave. So out of these two waves, which actually uh, take place within the body of the earth, one wave is much faster than the other. So typically the P wave, which is called the primary wave, is much faster. It travels much faster. And because it can pass through any medium, whether it's a solid, liquid, or gaseous. Whereas the secondary wave, which in short we say called as the S wave, it can only pass through the solid medium. And what is dangerous for our civil infrastructure is the surface wave, not the body waves. So if you see actually the a cross section of the earth, so this is your center. So we know the inner portion is not exactly solid, it is in the liquid state. So as a result, the transmission of these waves are actually different. For example, if you see, if this is the focus, or you can see the epicenter of the earthquake, there will be certain area where the P and S wave will be observed. There will be some area where only the S wave will observe because, or there may be some area where there will be no waves, called the shadow zone, because your P wave is the one which can travel to any medium, whether it's a solid or the liquid, and of course there will be some refraction. So with this background, if you see actually typical ground motion record from any of the instrument we installed, typically we look at the acceleration records. So it looks like something like this. So this is the one where your first instance of your P wave, and then after some time you have the S wave, and both of them are a body wave. If you see the what is body wave, is essentially P wave is essentially consist of like pushing the medium, like the whether through dilation or the compression. S wave is something in the up and down kind of wave. So these two are the body wave. And if you see the bigger spikes are actually generated due to the surface wave, which this is one of the example of the surface wave where you can see the lower portion remain more or less intact. All the deformation happens at the surface. And this is the one which is damaging and which as an engineer, we should be concerned about this. And most of these design provisions are actually developed to cater the effects or the seismic effects primarily due to the surface wave. Um, if we know that like it is the energy release, we have the energy release in the explosion also. So I just wanted to actually give an impression here that if this is the signature of a wave, this you can clearly see this is the earthquake. There is a P wave, there is a S wave, and a surface wave. Whereas if you have a explosion like you have underground blast or above ground blast, the wave actually signature is quite different from the earthquake. This gives us a lot of information, and this is the probably the nature of the uh, you know the signature, because you have at one time you have P wave, then after some time you have S wave, after some time you have surface wave. The gap between the P wave and S wave actually gives us some kind of information to work on the earthquake early warning system. And that I will actually talk about briefly towards the end of this lecture. If we look at our India map, the earthquake hazard map. So BMTPC 2019 has come up with the hazard map of India for the wind, earthquake, all these hazards. If you look at the earthquake hazards, you can see these dots represent the events which have been recorded in the last 200 odd years. And these dots are actually, any earthquake having the magnitude, Richter magnitude more than 5. So 5, 6, 7, 8. And if you look at the major or big earthquakes, which have the magnitude of more than 8, there are a number of big earthquake that is having the 8 magnitude. And so in entire, India subcontinent, you can see there are many faults which are quite active, have the potential for generating the relatively more, bigger earthquakes. So what we are right now, that is called the current practice in terms of this design. So design we expect that my same structure, if there is a minor shaking, it is, after the shaking, my structure should not be damaged. I can use the structure immediately. For the moderate shaking, there will be some kind of damage which can be repairable and reusable. And same structure, if it is severely damaged, then what it can be, the goal is it should not collapse. So I can actually save the people who are staying, occupying this building. So the intention was to no building bridge should collapse for the severe, shaking. So what is the interest to us is there are many earthquakes of minor earthquakes happens, like, if in Delhi, you will see that every 1 month or 2 months, there are couple of earthquakes, which are minor earthquakes. But if there are moderate earthquake and major earthquake, the damage should be such that which will be controllable in a controlled manner. And that should actually, that depends on how good we have designed our structure, where we can actually, at what level of damage we can allow. So that is essentially the current earthquake design practices. So to give a very overview of this earthquake resistant design, so if I don't want my building to be damaged, so there is this basic philosophy currently in the earthquake resistance design, that during earthquake, it doesn't mean that my structure will not be damaged. So I allow my structure to get damaged, but it should not collapse. So there is a difference between damage and collapse. The term damage means anything you actually, which is not a linear response. So because of there are inherent, structural characteristics or the material characteristics involved in the concrete, steel, masonry we use. So we can always rely on the nonlinear response of the structure. And so, in a sense, if I, for example, Taj Mahal, like if you know that the Taj Mahal is standing for a long, so that without any damage in probably like, relatively moderate earthquake is an experience. Because if you compare the dimension of the wall, it is in terms of the meters. But if you look at our walls, our columns, they are quite, small. So the reason is like making a structure will not damage in the earthquake will be very, very expensive. The second one is there is no guarantee that during the lifespan of the structure there will be an earthquake. And the third part is, why I should actually restrain myself to design a structure to behave, elastic if I have a confidence on the nonlinear behavior or inelastic response. So typically what we actually expect that we reduce the force, but we actually expect that I should have sufficient deformability so that the area under this elastic behavior and inelastic behavior remains same. So we know that the force, if it is force and is displacement, the area under this it is called as the energy. So traditionally what we want to do is we try to equate the energy demand coming from the earthquake to the energies being actually either absorbed or the dissipated by the structure. And that is not by making a stronger structure, but by designing a structure which has sufficient deformability. So when I say that its deformability, it will be not linear. That means that there will be some kind of damage. I have to control the location of the damage. I have to control the extent of damage. And the one thing is very clear that how far I'm stretching my structure in terms of the displacement. That's why like the current design practice is based on, that is a term called the ductility. So which is essentially the, kind of measure from the displacement from your linear portion to the probably like the ultimate deformation level. So if I look at very common sense, like how a structure actually survive or behave under an earthquake. So it can be experienced or expressed in a very similar equation, which is called the energy balance, which is applied in all fields of engineering or science. That means your input energy must be equal to your output energy. So if this is my earthquake energy, and so essentially coming from your earthquake, and then this part is what is your structure is experiencing. So so the output is combination of the strain energy, the kinetic energy, and each material has some kind of damping, so it also releases or absorbs some energy. And the most important point is, because the earthquake energies or loading is cyclic, there will be some hysteretic energy. I will come to this part in detail in subsequent slide. So if this is the capacity of my structure, if this component is higher than this, then my structure will survive, otherwise it will fail. So in terms of the hysteretic energy, like what it means that like if I take a structure and pull it or push it, so if it is linear, this part is called as the energy stored, because if you release the load, it will come back to the original position. If you again apply the load, there will be a point when it will go to the inelastic range. And if you do the cyclic loading, so this shaded part, because this part will be kind of energy recovered, because it's essentially same as this area. So if you look at this part, this is it's a kind of rhombus, you can say, or the parallelogram. So this is the typically the area which is the energy dissipated. And that part, like if I have shown in one direction, if you actually draw a negative direction, that becomes your hysteretic energy under cyclic loading. So that is the strategy we use in the earthquake engineering. So the first part is either we reduce the intensity of the vibration by adding some additional damping, which simply called the damper. For example, like in your door, like we have a door stopper, right? When you open it and just release it, actually what it will come back to the original position, because of there is some damping involved, right? And so in the structures, we can use similar kind of concept is being used, that is called the damping. Or we can increase this component, which is called the hysteretic energy. That means we need to increase this, kind of flag-shaped area of that is called the capacity. So the more this area, that is the capacity of the structure, my earthquake resistance capacity of the structure is, it will be higher. So just briefly giving that what is the effect of the damping, it is, I give the example of your door stopper. Is mostly the damping comes from the term, or associated with the viscosity. This is called as viscous damping. And so we typically represent in kind of dashboard. So if you can see a structure, probably I can use two viscous damper here. And if you look at their behavior, like there is a force versus displacement behavior, this will be the area that is the energy being released or dissipated. And so typical viscous damper, which is used in the structure, they add essentially like, additional damping in the range of 10 to 30% in addition to the inherent damping. Okay, and the effect is like the more the damping, you have the faster degradation of your vibration effect. At the same time, and that helps me to, if I have a structure which is more damp, probably actually I can design my structure more efficiently, because the force demand required to design the structure is also reduces. So coming to the design, the current design, what we call as the ductility based, the whole goal is to control the damage, and the objective is to to give a life safety level of protection. That means no loss of human lives or the property. So that is the goal. And so in that process, we rely on this deformation or ductility. But it has some demerits, which in the subsequent slides actually I will explain. But let's say that whole idea is to increase this area, because the more the area, the the structure has more energy dissipation capacity, and it is better for my earthquake. So there are many ways to do this. So what we or our team actually is working on to making some cost-effective, solutions where the device we create doesn't require some power supply to get activated during the earthquake. At the same time, it will not damage your primary elements like beams or columns for the bridges, or your piers for the beams and columns for buildings, piers for the bridges. So the whole idea is how well we can utilize the steel. That means we allow the steel to yield. That's why I'm saying it's yielding steel. Why steel? Because the steel has it's more ductile, it has a stable material behavior, it is not a mechanical device, it has better long term performance in terms of aging or resistance to aging. So that's why, like, steel means any, whether it's a steel plate, steel bar, if we can actually utilize in a more a more technical or engineering way, so we can actually increase this energy dissipation capacity. So the second point is the same steel plate I can actually design in a such way that the plate will take the axial force, or the same plate will take the shear, in plane shear or outer plane shear, which is the flexural thing. So essentially, this is, the goal is to exploit the steel, so that because your steel, that the mild steel I'm talking about, you have the strain, the failure strain more than 20-22%. So if you have that much of deformability, if you have that much of deformability, so we can utilize this to design our systems. Now, since I'm talking about the energy here, I'm talking about the increasing the area here. What happens to the damping? Because I'm not using any kind of viscosity based, fuse here, because viscosity has, viscosity, for example, door stopper, it has some life. It requires some maintenance, which is not there in case of the steel. So fortunately, if I am actually relying on the yielding of the steel, which give you this kind of curve, I can always, find out what are the equivalent stiffness, and I can always find out what is the equivalent viscous damping. And the most important point is this kind of devices are actually, the force generated is in phase with the velocity and directly proportional to the displacement. So if you actually say that the higher the displacement capacity, you have the hysteretic damping, whereas your viscous dampers actually mostly they are in phase and proportional. The force generated is proportional to the velocity. So based on this hysteretic damping or hysteretic energy dissipation, so the systems can be divided into two broad category. One is the anti-seismic systems, where you can see this, you have the beams and columns, but in addition to that, you have the diagonal elements, right? So, and they are actually installed throughout the building or throughout the structure. So we call as it's a stiffening structure. And in other type, like it is the small element you install at some floor levels, and the idea is to observe or to dissipate the energy at isolated locations. We call them the structural fuse. The difference here is this kind of system, both are anti-seismic, but these kind of systems are In one case, you get the stiffening effect. So it becomes stiffer, you get the energy, static energy, you get the damping. Whereas in this case, you get the energy and damping, but the stiffness increase is not that much. Typically, we call them, like in this case, we call them as fuse. I'll come to that, what is similar to the or analogous to electrical fuses. So if in case of stiffening system, you might have noticed that, many structures have some kind of diagonal element we call as the braces. And these braces are typically made of steel. And if you actually try to see that how they actually behave under earthquake loading, out of this, like at any point of time, one brace will straighten, that will in tension, other brace will in compression. And at some point of time, there will be a fracture of the brace. So if you see the typical brace hysteretic behavior, in one side, there is no degradation. But in the other side, you have, in subsequent cycle, your strength is actually going to reduce. If you see the area enclosed in this section, this is your origin, and the area kind of enclosed in this portion. So this much of area you are losing here because of the buckling. You know that buckling is a kind of instability which reduces your subsequent load carrying capacity. But having said that, it is one of the most cost-effective system and is mostly used in many of the steel buildings as well as the concrete buildings, also primarily for the strengthening or stiffening purpose. So what we we can't actually prevent the buckling of the brace. But what we can do is, if you see in detail, when say brace buckle, there are three potential locations where there are some inelastic behavior. Like typically there are three locations. One at the middle. If you see the previous one is here, one is here. There is some bending, and one is here. So these three locations are the potential locations where the excessive inelastic deformation takes place. So in the same brace, we try to actually develop a connection in a detailing, which, for example, before this connection fail, it will give you the additional energy cycles. And in addition to that, at the end of the brace, for example, here, we actually proposed one a simple uh, connecting or detailing system. It's similar to like testing your steel coupons, so that during the cycle loading this part, so some kind of detailing we can do here, which is based on the friction and your tension and compression. And the test results showed that in the typical steel braces, where these kind of braces can only sustain 2% drift level, this detailing which we have actually developed that give you story drift up to 5% without any failure. But please note that we are not trying to increase the area which is here, but what we are trying to increase here is we are trying to increase the deformability, so that the area, so in the previous typical brace frame, you stop here around 2%, you actually 1.5% you stop here, but in this case one can go up to 5%. So in that sense, you get wider area without any failure. So that improve your energy dissipation capacity. We have submitted one of the patent for this also, which is under review. Now, what building on this area, so the idea is, can't we increase this area? So that becomes, because it is essentially due to the buckling, the question is, can we prevent the buckling of this system? The answer was yes, it is possible. And theoretically, if you can, like if this is the traditional brace, and if we can prevent the buckling, the whole energy or the force deformation curve will be something like this. You can see the equal area is tension and compression. That is called the buckling resistant brace, and it is based on called as the higher mode buckling. So typically, like if you keep on adding the lateral support, your buckling, one support you add, your buckling strength increased by for example, at the middle it increased by 4 times. If you add 2, it increased by 9 times. So when you increase the buckling strength, it doesn't mean that there will be no elasticity, because the steel is a material which has nearly symmetric material property in tension and compression. So once you prevent the buckling, it will yield in compression as well. So this is typical BRB, which is being there already for 10, 15 years. So this is the core plate. And the only thing is so this is the plate which actually, or you can say brace, which takes care of the load or transport the load. And this brace is actually, or this core plate is around, placed inside a tube with some kind of motor, and so that like this core plate is free to move. But when this plate is try to buckle, this system which is encasing it, it will prevent the buckling. So this is, you can see the typical force deformation behavior of a typical BRB. But there are some issues with this. The first ones, these are the patented items, which means the manufacturer gives you give the data like how much, what is the force of the brace you want, and they will manufacture and deliver to you. So the question is like, if you don't have the manufacturer in India, you can't use this. The second point here is uh, this is system you can't see. Actually, the outer one is only to hold your main core. So after the earthquake, what happens to the core, it is not known. That means either you have to break it, that means you have to uh, buy a new BRB and do this. So these are some issues which actually came to our mind, like how to take care of this so that we can develop the low cost BRB, which should give you the lot of flexibility in terms of the installation, in terms of like fabrication, and as well as in terms of the post earthquake inspection, so that the same BRB should I replace or should I retain for the next earthquake. Typically, like these BRBs, the core plates have a good hysteretic or energy dissipation behavior. As you can see that the nice butterfly curves here, that means they have more or less similar load carrying capacity in the tension and compression. However, the problem is, let's say if you stretch your BRB during the earthquake loading, when there is a surface wave, you stretch here, and your earthquake is actually like, effect is gone. So that means it will try to come back to zero position. That means your BRB will at that position. So that you imagine that this BRB length is increased by some few millimeters. That means your building will be at a tilted position. So there is some issue with the permanent displacement. So with this, what we actually try to see, this traditional BRBs use the steel, some kind of casing. So what we work on using some novel materials and some additional elements. And what we did is we try to create a modular low cost BRB, which it's all metallic, which can be actually installed or in fact fabricated and assembled at the site. So this is one of the BRB which I'm showing here, which is nearly full scale we have tested in our lab. And all these are the bolted one. One can actually clearly imagine like this is a BRB which is installed in a structure. And after the end of the earthquake, you can actually go back on loosen the bolt, and you can see what is there in whether the core is there in perfectly shape or not. The challenging thing was like, how to remember that this will act as a BRB as long as your outside casing is not heavy. At the same time, it is a, stiffer one to provide or act as a, kind of restraining system. So this is one of the patent actually granted in 2023. We applied in 2021 for the low cost BRB. So if you go to the detail one, there are so many components involved here, but this is the one which is the load carrying capacity of this. So these BRBs are full scale BRBs of length 3 meter, 4 meter, 5 meter length. And I'm showing one of the tested results we did it on in our lab. You can see the nice curves without using any kind of tubes or concrete. It's simple low cost construction modules. Uh, Second part is the fuse. Fuse, I said, like is kind of small device. It can be actually, probably handled by a couple of people to the site. Sorry. So it is same as the electrical fuse. The role of the electrical fuse is it's there. It allows you to the complete the cycle. But when there is a higher load, the fuse actually burnt away, and so that your appliances are not getting damaged during a high electric load. So what you have to do is you have to actually go back and replace the fuse and put a new fuse there. So same thing, we have actually the concept of structural fuses. Like if you see this is your beam, column beam. So you install one of the fuse at the beam level. It can be installed at any level. I'm just showing for the sake of discussion. And the only thing is, although these two braces are there, which they should not be confused with the previous one. These two braces, the role here is to hold this fuse at its position. They just give a support rather than giving you some kind of energy. And so there are many ways we can um, create this structural fuse. Again, all these are passive device. That means you don't need your device to get activated during the earthquake. So the first part is like we typically till today the BRVs are developed in the understanding that there has to be 3 meter or 2 meter long to get a hysteretic response of this shape. Sorry. But what we did is we actually created short core BRB. That means it can say only 2 feet long BRB with some modifications. And again, using the steel, and which can be, for example, you have a column and beam system. You can actually simply connect a brace and your BRB here. And the typical that BRB, you can see this is one of the test result I'm showing here. Um, this is the test setup. This is the BRB you can see here. So it not only gives you the a nice hysteretic curve, you can clearly see that there is a higher mode effect is coming into picture. So the buckling is there, but they are not buckling in the first mode. So that's why they are not governing. So the similar force in tension and compression is you get through the yielding of the material. The other one is the same steel we can actually arrange in such way that, like, you can see there is a triangular plate and then there is another triangular plate, and in between there is a plate, rectangular plate. So they are actually placed in the perpendicular way. So if you think of pushing from here, so this plate will go into flexure or the bending, whereas this plate will go in the in-plane shear. So so we combine the shear and flexure or exploit the shear and flexure behavior of the steel plate. And this is one of the photo I'm trying to show here, so how they actually behave. Remember, the whole purpose is the fuse. We want this device to get damaged because they are simple steel plates. It can be easily fabricated there. And with this, you can see that you will get the strength, the force, and the displacement, and at the same time, it is the energy. But you can see that there is some tearing is being taking place here. So it has a limitation that how much drift you can get. So the second or the new device which we develop is we actually try to see that what happens to the center or core plate, this plate here. So if you see this video, actually, like when there is in-plane shear, so this your web plate is actually deforming to in the outer plane direction, and without any kind of crack or instability. So the idea is, if we allow or develop a mechanism to prevent this outer plane deformation while allowing the in-plane displacement, so we can get the desired strength, stiffness, energy. And you can see one of the photographs without any kind of outer plane deformation. You can see there is some fracture is taking place. And we can also delay the fracture because in the earthquake loading or earthquake shaking, the fatigue behavior is also low cycle fatigue aspect is also very important. So it's same as the previous one where you can you can think of that there is a device installed here, but this device is little different from the previous one where there is it looks like there are so many stiffeners here, but the main energy dissipating element is actually sandwiched between two assemblies here, and there is a gap here. So you can see there are four parts, and these four parts are actually connected in there are many parts actually, but they are connected in this way. So this is the C is the centralized element, which is some kind of can be any kind of shape that I'm coming to the next slide. And then it is sandwiched between two plates, and then finally you have this on the left side, and this one is the right side, and this is bolted connection. So to get this shape, we did the shape optimization. That's number one, that what is the best shape you can get to maximize your energy dissipation capacity. The second one is you usually get a plate and make it during the fabrication, it cutting and something. And what we see that the thermal, like when you cut the plate, there are some heat generated, and it actually reduces the ductility a large extent, even how small it is. So what we actually did is we used a technique called the water jet cutting technique, so that your material characteristics are actually least compromised during this process. The shape we develop, and then we play with the different materials like let's say steel and aluminum, and then it comes out with this kind of shape. We tested around 30 such dampers, which is called the buckling inhibited shear yielding and dampers or shear yielding devices. I'm trying to show one of the video how it actually look like when during the earthquake condition. You can see the lower one is fixed and the upper one is moving, and the main core plate, which is not visible, this is actually moving actually left to right under in plane shear. And these are the sample results I'm showing here. This shows what is the maximum strength, maximum strain it can actually or the displacement it can take. And you can see the up to 15% they are good, and one can also rely up to 25% you can have the better strength. It And this one is for the low cycle fatigue. You can see that the same specimen actually sustained at least 90 low fatigue cycles before it fracture, and that is around like any device which have around 100 or 90 to 100 low cycle fatigue characteristics is assumed to be best or good device for the earthquake applications. So till that point, what we are talking about the current practice. So that means you allow the damage to be there in the structure, but uh, at the same time, you don't want your primary elements to get damaged. You want to dissipate the energy so that your beams and columns and walls are actually not subjected to that the heavy force, or so that the damage level are controlled. But the second one is can we do something in the next step that is called the resilience, that okay, if there is a seismic event, there is some damage, then your functionality is lost. And in the current practice, it will not come to zero, because what we are expecting that there will be there will be some position where this called the it has some residual functionality. For example, think of a building which is greatly damaged. So it is not collapsed, so there is no loss of the life. But utilizing that building again to or bringing the building or bridge again to the its original shape, you need to actually wait and take the decision, do the repair, and then you maybe have the full recovery. Or at some point of time, you may actually come to the partial recovery. So the resilience is the term is how well it can recover to its original functionality, and within minimum elapsed time, right? So from this point to T0 to TH, let's say, that is the point called the resilience. Like if we can minimize this, so we can use the reuse the structure, more, more, or maybe more, earlier to the what we follow the in the common practice. So how to do this? So the idea is, can we design or can we install some of the device which will not damage my structure, or even if it is damaging, it will pull back my structure to its original position. So the next level of design, seismic designing, is called the resilience based or the recentering based. That means you stretch me at what level it is required, but at the end of the day, I should be actually come back to my original position. So that is called the fully operational level. So if you remember, the ductility based design is the life safety level, whereas this design concept is called the fully operational level. Means during the earthquake or just after the earthquake, the building can be made operational without waiting for the repair or retrofitting. So if you compare the previous one, so this was the dashed line. So whole idea was to increase this area so that more energy will be dissipated. My structure has better capacity. Now that is for the traditional yielding system. So what we are talking about, the self-centering system. That means this shaded area is the area or the static energy is being dissipated. But the moment the earthquake is gone, it will come back to its original position. That means in the previous case, probably you will be here. That means your building or bridge will have a tilted position. But in this kind of system, like there is this mechanism which pull back the system to the original position. So under this, I'll try to show a few devices which we have worked on and we have actually tested as case studies. So how it worked, like take the example of the BRV part. So in one sense, the BRV, which is the ductility based, what essentially is required that to pull back to its original position, and that means you have to add a self-centering system. And the self-centering system, there are many options. The best options are actually the shape memory alloy material you can use, or there is some anything based on the post tensioning. So if you look at the self-centering system, which may be due to shape memory alloy or some kind of post in a combination of the pre-tensioning or post-tensioning rod. So let's say this is the behavior into force and displacement. If you combine both of them, it appears to be something like this. Okay, and that is the target we want. So okay, ideal case it should come back to its original zero, but in case you are actually getting here, that is good that try to minimize the residual drift. That means the building is, or the bridge is not that and not habitable after the earthquake. So before I go to the BRV part, let's talk about the shape memory alloy. So shape memory alloy is typically a material which actually it has the capacity to generate the pre-stressing force when you actually apply some kind of temperature, and it has actually it's called the phase transformation. It has two effects. One is called the shape memory effect, and that means it actually remember the path it traveled. At the same time, it has a super elastic city effect. So it has essentially you can control the temperature, you can cool the uh, apply the temperature on the lower side or higher side, so that your martensite phase actually becomes a austenite, and then vice versa. So it has a reversible phase transformation under the temperature loading. So if we can actually utilize the super elasticity behavior and make some kind of device, that means that is what I was looking for, like this, something like this. So that's why the shape memory alloy was actually chosen for developing these braces. So however, the issue was, shape memory alloy is not available as a plate and it is, first of all, it's not available in India, unlike steel. The second is there is limitation in terms of what you get in the Indian market. So what we try to do is we actually explore two alternatives. One is, of course, using the shape memory alloy. And at the same time, we actually tie up with one of the industry, and we say that can we combine the shape memory alloy characteristics with the steel? And the whole idea is, if you see that with the steel, this is the behavior of the steel, and if we can change the chemical composition, we can actually hold this super elastic material, which is called the iron-based SMA. So it has the strength greater than the steel, and at the same time, you can see when you are actually unloading, you have the, or you minimize the residual drift or residual deformation as compared to the steel. So the configuration we actually selected is again all steel to steel. This is one configuration I'm showing. This is a plate which is not a steel plate. It's not a shape memory alloy plate. This is a Fe based iron based SMA core plate. And the issue, it has some issue because it has it is near in between the iron, steel and SMA, so it is sensitive towards the temperature. So welding was one of the issue, and then we tried to manage how to deal with making our device. So and the second stage, what we did was, we actually, instead of making one core, we actually try to explore, can it be multi-core, so that your history behavior, rather than a butterfly one, it will be a stepped one. So that whole idea is it will dissipate the energy and it should come back to its original position. So this is called as the iron based or Fe based SMA BRB. So this is it's not a real length of the brace, but in terms of scale, it's quite large scale brace. We tested a couple of them in our lab, and this has been so this part is what I'm talking about, the BRB part. This can be one BRB or this can be simple tube also. But here we try to use the iron-based SMA, so that you will get some recentering. So this is one of the patent also is accepted in last year. Many times, like in the bridge applications or the beam to column applications, we thought of like, if instead of a rigid connection, can we have something like without damaging the connection? So that means, can we utilize this material to make small energy dissipating devices called the miniature BRBs? So for this, we actually created very small damping systems. Again, this is Fe-based SMA rod. In the previous case, we used the plates, and then we actually used the rod and tested in the UTM. You can see that this is the restrainer based, and then this is one of the videos showing how they actually perform. And you can see that, like, again, how small it is, they behave pretty well. They give you the 7% drift, and before fracture, you can see there are higher mode effects which we expected, and it has a better cumulative ductility of close to 500. Now, coming back to the SMA BRB, since there was no plates, typically the SMA is made of nickel titanium material, is a combination of two components. So we use the nickel rods as the SMA. The idea was to use the BRB and SMA in parallel. That means inside BRB and outer side the SMA rods. Remember, it's a rod, so you can always pull it. If you push it, it is the load carrying capacity is a concern, because it can go with out of plane deformations, not necessarily buckle, but yes, it can go in the out of plane. So the whole challenge was like, can we combine these two things? Because your BRB, you need to go from tension to compression. But for the SMA, it can only take the tension. So you need to give first the pre-tension to your SMA rod. At the same time, they should work in conjunction with the BRB. So we use the double tube system. The one tube, inside one tube BRB, the other tube is the rod. And I'm trying to show one of the video here just for the explanation. You can look at the rod actually. The rod is at any point of time, the rod is in always in tension actually. And at the when the BRB is extending, the rod is in tension. When the BRB is compression, is in tension. And because there is a load transferring tubes, which is transferring the load between the BRB and the rod. So this is more detailed explanation of the BRB tube. sorry, this is the SMA rod. And what we also did is, because the SMA is quite expensive, we actually minimize this length aspect, cost by adding some rigid rods, and then this part is SMA. This is, you can see the final product is this, and this is one of the device we tested in the lab, and this is the nearly kind of linear behavior we get with proper recentering due to this self-centering brace. This is again the patent we got approved last year. So since a couple of times I said the getting the SMA is not only tough, it is expensive. So we also try to use the same technique using some kind of carbon fiber composite cables. The concept remains same. It is the same concept we use in the post tension bridge girders actually. And so the whole idea was to bring back your system or a BRB or your whole structure to its original position. So this is more detailed about this. You can see clearly here that this is the hysteretic behavior, and once you because of the recentering, you are closely or nearly coming to the zero position. That means your residual deformation is pretty low. So last part of this self-centering system is going back to your ancient structures. So probably most of the Greek structures and in Chinese also, like you can see some of these structures. Though one of the interesting thing is like there is no physical connection between this member and this member. So, and sometimes there is no physical connection between the column to the footing. So it is a freestanding column-based structures because of the weight, uh, uh, but they have already sustained many earthquakes. So the idea was how they behave is through rocking, and other one is through actually sliding. Like if the whole part is sliding, so there will some friction develop here. So you have the frictional energy, and the energy dissipated through the frictional action, and then because we're rocking, because it is not rigidly connected, it will rock and come back to the original position. So, taking that clue actually, so what it is actually, um, you know, planned is like if you have a building with a foundation, let's say the mat foundation or the podium, like it can be actually not directly rest on the ground, but instead, it can be rested on a series of, you know, very rigid columns. So the how to define these rigid columns. So most of the best example is concrete filled tube columns, like the tube filled with the concrete. And when there is earthquake, you can see that this is the rocking position, and they will rock about the mean position and come back to the original position. And or it can be combined with some of the device which we have discussed over previous slides, either BRB or some kind of post tension or pre-tension rods. The other application is like if you have multiple towers of steel structure or concrete structures, so same devices can be actually connected at the interface of this, so that when they are actually deforming from left to right, so there will be deformation. So deformation is kind of dissipated through, or the energy dissipated through these devices. So or the concept is, instead of your traditional column, your column is a damper. Like it can be BRB damper, it can be friction based damper, and or it can be anything on the pin actually. Similar thing, it can be also for the bridge, so whether it's a rocking segmental pier or a monolithic pier, but you can see there is no physical connection here, but there is a pre-tension or post-tension rod here. And of course, to make the stability and increase the energy dissipation, we can actually use the small dampers here at the base. So these are few more applications for the kind of device I'm talking about, whether it's the BRB, whether it's the buckling, the shear yielding device, or self-centering BRB, or simple shear yielding devices. So there are some applications and case studies actually I want to show here. These are some BRBs, installed in the real life structures. This is one building where the BRB actually used to retrofit or rehabilitate for, this is a highly seismic zone. And this is one of the building in New Zealand for the Christchurch, where the BRB is used to upgrade the structure after the 2007 earthquake. And this is a typical structure which we test in our lab. In India, we have a concept of the ground floor is called a stilt, where we use the park, the structure, and all other structures actually, all other floors we use at typically for the walls or something. And this is stilt kind of building we called, and these buildings actually are very, very vulnerable to the earthquake. One of the best example of the Bhuj earthquake, there were many such buildings actually collapse. So you can see there is nothing at the ground floor because we usually park here. And then you have the continuous other top floors where you have the masonry walls or something. So we try to see that, like, while we know that this area is, we can't actually cover this area, what about installing some of the devices? So we use the simple shear yielding device, and you can see that it gives you a better result. This is probably like nearly full scale test and one of the first large scale test on the two-story building in India. Again, the same BRBs, currently it is used for the steel building and very limited RC building, but for the reinforced concrete buildings and the bridges, it can be applied with little bit of connection at the ends. For the retrofitting also, we can go for the self-centering brace or the conventional brace or the iron-based SMA BRBs. This is one of the brace we have discussed, but this can be used for the upgrading of your any deficient buildings. For high-rise structures also, like this is one of the potential location where you can use the BRBs to reduce the vibration effect and the damaging effect of the earthquakes. For the buildings, bridges, I have already explained, like at the joint or the connection part, you can use the miniature BRBs, some kind of rod type of small BRBs at the connections, so that you don't need the rigid connection. So when there is the tilting or the vibration of the building, that you can see there is a gap. So because there is no physical connection between beam and columns, and this gap actually taken care of by your BRBs in terms of tension and compression. So my last segment is the what is the future direction or challenges ahead. So I think the primary objective is like to use the minimum material and get the one of the best or efficient damping device. And sometimes like we need to use some technique called the magnification, so that how to include some kind of algorithm to magnify the damping force, or we can actually create some new materials for the hysteresis damper for the passive control. The more work is needed to be done for the high performance devices with or very low energy supply, because see, during the earthquake, if your device is relying on the power supply, so then there is a problem. So the most of the work I do is towards that aspect, that it has to be the passive based devices. The second one is the disaster risk reduction, because we have a understanding of more or less the Indian subcontinent, or the fault location, the type of fault, what is how big earthquake the fault can generate. And then we have that is called the hazard signs. And then we have the exposure, like what kind of infrastructure we have, what are the demographic effects. So taking this into account, one can calculate the vulnerability, and from that one has to create the loss matrix. Loss matrix, like unlike the seismic zonation, which is more towards the hazard signs, the loss matrix will be quite helpful for different cities to give an idea to the government to prioritize the action need to be taken or during a disaster, or which area need to be focused on, because based on this analysis the expected loss in terms of the people affected, repair, replacement, or business interruption will be higher. So this is decision making. It will actually make a lot of impact if you do that kind of analysis. The third part, which is pretty interesting, I start from this, that you have a P wave, you have a S wave, and then you have a surface wave. And if you see the record, there is a time gap between this P wave, which is relatively smaller, to the surface wave. So this time is very, very critical. We can't predict when this P wave will reach, or no, what date, what time. But what we can do is, whole idea is, can we capture this time? Because most of the cases, P wave and S wave are not damaging. So if we utilize this time and then sensitize, do the real-time probabilistic seismic hazard analysis, and find out in which direction the waves can go, which city it will impact, and then all the civil infrastructure can be connected, like wide kind of advertisement we can do through the television or something. Like, it is there in the metros, that the metro automatically stop the time it gets the sense there is a vibration. Or but what I'm saying, that before that happen, during this time, it since a lot of information we have already present, this time can be utilized to sensitize to people, to reduce the loss of the human life or infrastructure damage in the event of earthquake. That is called the early warning. What we are actually at this stage, we take the data, we do the real time probabilistic seismic hazard analysis. What we should or to work on to take this data, connect to the, for example, bridges or the metros, or we can also create this different scenario for the loss estimation real time. That is called the next generation early warning system, which we should work on. This is end of my presentation. Thank you so much. I think I am in time.
So, Professor Sahoo, you have given a very, very elaborate presentation here, starting from earthquake to earthquake resilient system, so many devices. All these things are not known to me, because I am not from this discipline. But definitely, this was very, very interesting lecture. I have got a couple of questions. So first of all, let us say this country like Japan, Taiwan, almost now and then earthquake is there, but the damage to their structures, building in these countries is actually not that much compared to how much of compared to other places. So my question is, what type of design this Japanese and Taiwan they use, so that the effect could be minimum? Some idea.
Yeah, I think it's a very good question actually in the context of this lecture. So the first of all, like in the Japanese construction practice are actually quite different from what we follow in India. That's number one. But Taiwan is more or less similar to what we have been actually doing in terms of the construction materials I'm talking about. In Japan, like most of the structures, they make timber structures, kind of thing, wood structures. But if I talk about our, society is more towards the concrete, masonry, all these things. in India, actually, construction practice is an issue. I'm talking about, you know, mostly for the residential structures, where many there is a huge number of structures. There is a construction practice. The second is for the quality of the construction. That is number two. Number three is it's not that the buildings in Taiwan, in recent earthquake, the buildings were not damaged. They were damaged, but the damage was controlled by using some techniques and better construction practices. So both things are important. One is construction practice. The second one is the adoption of the techniques, actually, which are available nowadays. Like, every country actually started from a rough estimation on the earthquake forces to a more precise estimation of earthquake force today. But how we change our code, how we change our practices, and how we can bring to the society, like to our mason level, that is one of the a long way to go in the context of residential structures. And in terms of the commercial structures, high-rise structures, the point is, again, there a to some extent, the a good amount of a good construction practice is followed in many cases, if not all. But still we are lagging behind in terms of the technology we adopt. We are still to in many cases to our the conventional practices, where the technology has gone very moved ahead. So both the cases, whether it's the important structures, whether it's office buildings or residential structures, I would say the both things are quite important. We should take what is the current state of the art, and we should use the best technology in the practice, and then the construction practices need to be improved. And of course, the qualified personnel who are actually making this infrastructure. These are the three difference I can see.
I've got a second question. The question is, you see, this Uttarakhand and that area is earthquake prone, but still on the river, they are constructing so many dams. Okay. So what is the precaution they take? What type of devices they use? Because its consequences will be very, very dangerous. The same thing is also true for nuclear power plants.
Yes. So these two are actually little. So nuclear power plants, actually, the safety level or the design level is at a different scale we talk about, because that nuclear disaster is probably like, it's not controllable. So I believe that nuclear power plants, if it is being constructed on the earthquake prone areas, most of the nuclear power plants actually are not in the earthquake prone areas, but if it at all they are. So the um, uh, I'm sure the adequate safety level is being taken, or because that is one of the if you will see the BRNS guideline, I went through this, so they have actually taken very stringent requirement, which is quite very high in terms of what is there in the practice. So nuclear power plants, in terms of earthquake effects, I think that is being taken care of. Coming back to the dam aspect, so one is your building, or bridges which are actually located in nearby areas. The other one is what is happening there in the recent news, actually, like because of some settlement and all these things are happening. So it is little complex, quite complex, I'll say, because most of these buildings are again, they are not on the levels, they are in different levels in the hilly areas. So that makes many of the structure is more vulnerable if I assume the similar construction materials, construction practices are being used. So I think those structures located in these areas requires the highest level of attention before we actually proceed for anything else, which will further damage the safety of these structures. But I am not involved in those projects, so I have not seen things. So I can see in very generic sense what is happening there.
Okay. Any other question, please?
Dr. Acharya, can I ask a question? Am I audible?
Yes, you are audible.
Yes.
Dr. Sahoo, thank you very much. In a short time of 1.5 hours, you have put in so much information that as you were talking, I was getting some questions. But now I cannot ask all of them. I have to come and attend your class in order to understand everything you said. But I will try to ask now, because there is not too much time here. I'll try to ask some only 1 or 2 questions. I go to your shape memory alloy, last item that you talked about. As far as I know, shape memory alloy has got nickel and titanium. It is titanium and nickel. With just nickel,
Yes.
you cannot have a shape memory alloy, right?
Correct.
So now shape memory alloy, you format it, but when you want it to come back to its original condition, you have to heat it or cool it. You have to give a thermal load. So in your system, I don't see any heating cooling system there. So how does it return back? Shape memory alloy is not a spring. It will not come back on its own. So you have to give it a heat treatment, only then it will come back. Am I right? If that is so,
Yes.
what is there in your system?
Yeah, so it's a very good question actually. So the first of all, right now we are not applying any heat here. So that's the absolute bringing it to zero or fully exploiting the super elasticity or recentering capability of SMA is not we are actually investigating here. The first of all, like we are looking at if it is made, like it will be implemented in the building or bridges. Now in that building or bridges, where to heat it, like, so you need the heating to do this. So what we did is we first we use it, kind of some kind of pre-stressing we used, and on in the normal temperature actually, so room temperature. So we want to exploit that, and as you see that we will not get the desired shape memory alloy, the characteristics fully, we can't actually exploit here. But if I go to the next, which I have not included here. So what we have seen this not in the large scale, in the small scale, we did to actually exploit this one. We did a shake table study where we use the real amplitude. So these are the slow cyclic because you apply the cycles very, at certain rate. But when you have the earthquake, it is random. It is very fast. So we try to apply some of the some segment of El Centro earthquake, and we did the shaking table study. That during this process, the earthquake process, effects, is there any temperature change in the SMA? The answer was yes, but that temperature was not adequate to create that phase transformation actually to take place. But it has some effect to increase what we are getting in the slow cyclic loading case. But I completely agree with that. Like to fully exploit that ideal super elastic behavior, we need to have the temperature effect. And in practice, in the lab, we can always do this, but we refrain from doing that because in practice, it is many times it is not possible. So that's why we have not used the temperature effect here. We try to utilize, what is the super elastic capacity in the working condition. I hope I clarify your question you asked.
Okay, thank you. Now I will go back to your first slide where you showed a strut which is deflecting. You know that cross strut which was deflecting, not this, the cross strut. You showed the strut itself and it was deflecting. One strut goes on tension, the other set goes on compression, you said.
I see.
That,
Yes.
And that collapses. Now, if you know where it is going to buckle, can you not locally increase the moment of inertia there so that it doesn't buckle?
See, yeah, I think you're talking about this video. I think my slide is shared, right?
Your slide I'm able to see, but this is not the slide I'm talking about. Earlier you showed, you know, a parallelogram going like that. One side is in tension, one strut is in tension, the other one comes in the compression and it buckles. Anyway, doesn't matter. You said that you put two struts, no? So in that, one side goes in tension. When the building tilts, one side goes in tension, the other side comes in compression, therefore it buckles.
Yes.
So now what I'm trying to say is if you know where it is going to buckle, then can you not increase the moment of inertia at that area so that it will not buckle there? That strut is there, but it's locally increase the moment of inertia there.
So actually, see we can always do in ideally condition, but if we locally increase the moment of inertia, every member has the geometric imperfections, right? And that geometric imperfection will actually push the structure to buckle at some other location. It will buckle, but
okay. You
yeah.
can't predict so much. Yeah. Okay.
Yeah. So
right,
because of the geometric imperfections is there.
Right. Then next question. I have got two more. Next question is something that will increase your cost. You are worried about cost. I'm going to give a suggestion. Maybe you can consider. There are some stainless steels which can take 17% elongation. Before yield and up to ultimate strength, they've got 17% elongation. There are stainless steels that are made in India also. Nidani makes it. Of course, they may not be available in plate form. They can make it in plate form if you really want it. So this is called 17 4-page stainless steel. We use it very large. We used to. So can you not try to increase the material property? It's stainless steel. It will cost you more, but it may give you much greater flexibility because it will have much greater the hysteresis curve will become much bigger. Is it reasonable? What I'm saying?
Yeah. No, I think I'll take this suggestion. I'll explore this. Actually, I had a couple of suggestions on the stainless steel, but I have never worked on this area. So I'm keen to look at that.
ASTM A grade 564. ASTM A grade 564, grade 630. Nidani makes it in rods. So you can get them to make it in plates also, I'm sure. Or you can get it re-rolled somewhere else. And of course, it has to be heat treated and put. If you are making small struts in your, for example, in your fuse, you could use it in your fuse so that it will yield more.
Yeah, that annealing process we have in place. For example, like for aluminum, we did that. The annealing process to make the material soften, so increase the ductility. So that is not a concern. But thank you for
aluminum this. Aluminum will not have strength. It will not have. No, this is stainless steel. It will take close to 28,000 psi. You know, something like that. Very, very large. Ultimate strength is very high for this, so it will not fail that easily. 17% elongation it will give you.
Yeah. So for the FESMA, I can tell you what are the yield strength was around 900. So and ultimate strength is around 1050, close to your pre-stressing kind of thing. So the high strength steel. So that's why we focused on this Fe based material. It was 887, very, very specific the kind of material we got. And sometimes the ultimate strength is way above 950 also. So in some materials. Yeah, but I'll see this.
Unless it is cold rolled, you may not be able to increase the ultimate strength. You'll have to put carbon or any other thing. then ductility will go down. That's the problem with
Yes.
iron steel. This stainless steel is very good. Now, one more. Dr. Acharya talked about a nuclear. So I am a nuclear man, or was a nuclear man long ago. So now, what I wanted to tell you is that the time difference between the P wave and the S surface wave, you said there is some time difference. That will allow you to take some action. For example, trains to stop or something like that. When we were doing Kakrapar reactor, our regulatory people said you stop the trip the reactor when you sense an earthquake. So we needed to sense an earthquake 30 kilometers away from the reactor. That much distance we have to give it for the wave to travel to come to the reactor. So before that, you trip the reactor. So we were trying to put seismic trip, which we call seismic trip. We were trying to put, and as long as I was in office, that didn't. We were not very successful at that time. Maybe now they have put, but it is 30 kilometers. But we were having only 2 seconds time. It has to be done within 2 seconds. So I don't know what is the
Yes.
time difference you are having. If it's very small, nothing can be done.
I completely agree. But again, see, it is not only the time, your all other systems, your real-time probability seismic hazard analysis system, how well your document, hazard analysis has been done. So all these actually, are, need to be done simultaneously so that to have a more precise
Yeah.
attempt
No,
to have done the early warning system.
the first step is to trip the reactor so that it doesn't produce any more nuclear energy, nuclear thing. That is the first criteria. Then everything else is supposed to stand. Then, okay, so I will finish here because I've taken already too much of your time.
No, thank you, sir. Thank you so much for this nice insight.
So now
Yeah,
actually we have got another person, Viswajit, who has raised hand. Viswajit? Yes. Please ask your question. Hello.
Biswajit Chand ji, do you have any questions?
That's right. Somebody has actually raised his hand.
Yes, sir. But I don't know why he's not responding.
Anyway, he might have some other reason. So we had an excellent lecture by Dr. Sahoo, and at least we enjoyed it. Now I will have one or two formal questions. So Dr. Sahoo, your entire lecture is recorded. Do you have any objection if we share with others?
I think it should be fine. I don't have any objection as such.
Pardon?
I think it's fine, sir. I don't have any objection to this.
Okay, then we can definitely share. Now, one more thing with this, as a sort of token of appreciation, one memento actually will be sent to your address.
Okay, sir. Thank you so much, sir.
Now, I will request Professor Renu Sharma to present a vote of thanks.
Thank you, sir. Honorable Professor Damodaracharya, Chairman, INE Bhubaneswar Chapter. Honorable Professor P.K. Nanda, sir, Vice Chancellor, Shiksha Anusandhan deemed to be University. Honorable Directors of CSIR, MMT, IIT Bhubaneswar, NISA Bhubaneswar, Chair, IEEE Bhubaneswar Subsection, distinguished INE fellow guests, esteemed faculty members, and my dear participants. It is with profound gratitude and immense pleasure that I extend my heartfelt thanks to Professor Dipti Ranjan Sahoo sir for gracing us with his insightful lecture on anti-seismic device for earthquake resilient infrastructure. Sir, your expertise in the field combined with your passion of enhancing the resilience of structures against seismic activities has enlightened us all. Your lecture has been a beacon of knowledge, shedding light on innovative approaches and the techniques that are crucial for creating an infrastructure capable of withstanding formidable forces of earthquake. The depth of understanding you shared, coupled with the practical insight, has undoubtedly enriched our understanding and inspired us to pursue excellence in our respective domains. I would also like to express my gratitude to all the organizers of this distinguished lecture, including Annie Bhubaneswar chapter, SOA University, CSIR, IMMT Bhubaneswar, NISA Bhubaneswar, and IEEE Bhubaneswar subsection. With a collaborative effort in bringing together such a distinguished speaker and facilitating this enlightening session is really commendable. Once again, I extend my sincere thanks to Professor Dipti Ranjan Sahoo sir for his invaluable contribution and to all the organizers and the participants for making this distinguished lecture a resounding success. Let's carry forward the insight gained today to contribute towards creating a safer and more resilient built environment for generations to come. Thank you. Jai Hind.
Friends,
Thank you,
actually,
sir.
I have got one information to pass all of you. In next 1 month, we have scheduled 3 lectures. And the first lecture actually will be on 17th, and it will be given by Professor Parthapratim Chakrabarti, who's a sort of stalwart in AI science. Okay. The second one, most likely it will be given by Professor Ashok Gupta, that is in civil engineering area. And the third one is again by very stalwart, that is Professor Pradeep Datta of Indian Institute of Science, Bangalore. So these are the things actually in the pipeline. Please join, and whatever registration formality that we are doing, we will look into it, how this problem will not be there in future, as some of you have tried. So thank you very much, Professor Sahoo.
Thank you, sir. Thank you so
Thank you
much.
again so much for giving me this opportunity.
Namaste.
Thank you. Namaskar.